Well, hello there and welcome along to a little revision video on the processes and landforms associated at the different plate margins that we've got around the planet. I'm going to populate this map with the location of the plate margins as we go through. Right, first thing that we're going to do is just basically to set the broad context of the processes at work here, because this basic diagram, which is the diagram that we got for the processes that cause plate motion, sets the foundation for us for the different plate margins and underlying the processes. So here we have our ridge here, and it noticeably thins, if you remember. That's how to draw that basic diagram. And in terms of that basic diagram, what we want to get here are the processes that are moving the plates, just to clarify our understanding. So plate motion is driven largely and primarily by slab pull. This is as the cold, old, dense plate subducts down into the asthenosphere, into the mantle. It pulls the overlying plate along with it. As a result of that, you get tension here, which thins the plates, which allows the upwelling of the hot mantle rock in underneath, the generation of magma, which then injects itself into the plate above. That new sea crust, the new sea floor, is young and hot, therefore it's buoyant, and it rises up to form the ridge. And you get the material sliding down under gravity off the edge of the ridge. And that is your second process of ridge push. Those are the two main processes that move the plates, with slab pull being the dominant one. Okay, so with those processes in mind, let's go on now to take a look at some of the different plate margins that we need to study. And the first one that we're going to begin with is our destructive plate margin here. Now, to have a nice little simple diagram of our destructive plate margin, it's going to look something like this, of course, isn't it? So if we start off on the most basic level, this is what we've got here, the bending down of the non-subducting plate, the dipping down of the subducting plate, like so, and that's our most basic of diagrams. And the processes that are happening here, this is coming down this direction here, and this is moving this direction here. Now, in terms of the landforms that are formed at this location, you have got the trench, and you have got the volcanic arc. So how do we form the trench? And we have a trench here. Okay, so the trench is formed whenever you get a couple of processes operating here together. I wonder, can you see this from above? But I'm holding that piece of paper, and as I hold that piece of paper, the front end of it will bend down under its own weight, kind of like that. It's going to bend down under its own weight. And that's basically what's happening here as the subducting plate falls down into, or moves down into the mantle. This end here will bend down. Let's see, get this right there. It will bend down like that as it's falling down into the mantle. As it does so, friction between the leading edge of the non-subducting plate and this plate will cause that also to bend down. And the shape that we've just formed there is our trench shape. There it is. So it's the subducting slab bending down, friction with the overriding plate causing it to bend down, and that's what forms the trench. Now, just while we're here, of course, that's also what produces your megathrust earthquakes, because that pressure, that stress that's building up in this plate suddenly flips up, and that produces your megathrust earthquakes. But it's that bending down here and the bending down here that produces the trench. Then, whenever we move over to the volcanic arc, how is it produced? Right, as the subducting plate travels down. The pressure forces the water out of the subducting plate, was picked up whenever it was underneath the ocean there. And that causes partial melting to produce magma going up in these shapes, diapiers of magma, which will then inject into the plate above, forming the magma chamber. That will erupt out at the surface, and successive eruptions produces your volcanic island. Now, if this was a 3D image, that island would arc, as would the trench. You always get these arcing shapes in these features, so it's the volcanic island arc. But that's the most basic version of it. Those are the core things: the formation of the trench and the formation of the volcanic island arc. Now, if you have time, you can also talk about the accretionary wedge that is located here. It's the sediment scraped off the top, but that's an optional one depending on whether you've got the time. Right, that's the key thing for our destructive plate margin, and that's the variation that has ocean to ocean. The second variation of that is ocean to continent, and it's going to look like this. I'm getting my headset out of the way a wee bit. Okay, so we're going to have our continental crust here, and we're going to have it built up more like mountains here. It's going to be thicker because continental crust is thicker, and then here comes our oceanic plate coming down here. There's our trench again. Oceanic plate comes all the way down. Remember to draw that all the way down to the bottom. Despite the name destructive plate margin, the plate does not melt. There it is there. And we'll just put in the water here. Why don't we? We probably should put in the water here too, because this is ocean, so just for completeness sake. And a lot of the processes are very, very similar. So the process that forms the trench is exactly the same as above. The process that forms the volcanoes on top of the mountains is exactly the same as above. You get your diapiers of magma come up into the crust, magma chamber, and then will erupt at the surface to produce these volcanoes. Now, this being a destructive plate margin with continent, and the compression here can also cause some faulting, thrust faults here, which help to create the mountain chain there as well. Also to note, the type of volcano that you typically get, especially here, is, do you remember? It's a composite volcano. The reason for that is because the magma here spends more time in the plate, in the crust, has more time to evolve and become more silica rich. That is the essence of your destructive plate margin. Again, if you've got time, you can talk about the accretionary wedge of the scraped off sediment there as well. Okay, so we're seeing here in this case, it's the role of subduction, which is really important in the formation of your destructive plate margins. Right, where in the world? Can you remember? Okay, so the Pacific Ring of Fire is definitely a location where we get a lot of destructive margins, all the way around here, all the way around here, all the way around here, basically. You get a little bit in here, and then back up here in the Central America. So Volcan de Fuego is our example of that, and remember, composite volcano, so very, very eruptive, all the way down here. And you're also going to get some destructive plate margin just here, the South Sandwich Islands, and just round here as well. It's coming round from this bit here. So your Aleutian Islands, down here past Japan, the Philippines, down here Tonga, parts of New Zealand, Cascadia, Central America, South America, South Sandwich Islands, and Indonesia. And there's where you have your destructive plate margins, and these are the ones that, remember, can produce destructive, just write that down, can produce the megathrust earthquakes and your composite volcanoes. Okay, destructive. Next up, constructive. Okay, and in terms of your constructive plate margins, the main features that you're going to find here would be your mid-ocean ridge, and your central rift valley. Okay, so back up to our reference diagram at the start. We've got our subduction happening here, which causes the tension and causes the plates to thin just in this location. So let's see what we're going to add in here. So our basic diagram is, remember the way that I taught you to do this is to kind of sketch it in first like so, the overall shape that you're going to get. And just making sure you've got all the elements in there, and then you can ink in more deliberately and more precisely. Do bring some colouring pencils with you to this exam. And then we're going to have a series steps up to this. We're going to have our central rift valley. We're going to have our series of steps coming down. And then the plate has got to noticeably thin. Do over-exaggerate this, please. This is typically under the ocean, so let's put water over the top of it. Okay, so we've seen from our diagram here that this thinning of the plate allows passive convectional upwelling to occur just here. So the hotter mantle rock, which is solid but ductile, so it will flows up into this space underneath the thinned plate, and it experiences decompression melting, which produces magma. The magma is less dense and will rise up in these shapes known as diapirs, and they will then force its way into the rock as these dikes. This is magma. I'll just write down as well the decompression melting. Decompression melting, the key phrase there for you. The dikes will go up here and will then make the way up towards the surface, where it will erupt the surface as, do you remember? Pillow lavas, right? So this is low silica magma, so it's not as explosive anyway, and it kind of oozes out into the surface here. So think of what we saw when we were looking at the eruption in Iceland. It's very, very similar to this. Fissure eruptions coming out here, oozing out. It's effusive eruptions, and it comes out here and is instantly cooled by contact with the water, at least the outside of it, forming those loaves of the pillow lavas. Okay. Then the other feature that you need to be referring to here is the ridge. Now it's difficult on a diagram of this scale to get a sense of the width of the ridge, but you can be talking about something that'd be 1,000 to 2,000 kilometers wide. So it's very, very wide. And then in the center of it here, you have your central rift valley. And the central rift valley is formed because of normal faulting. Whenever you pull the plates apart here, when they experience that tension, the rock will crack, it will fault. But what you're doing basically is letting something go and it's falling down. So let's see if I can get something to illustrate that. You'll hear this from the noise. If I move my hands apart slightly, there was the bang. Let's do it even higher. There was the bang. And that central bit is falling down because the tension is pulling the rock apart, and when it breaks, it drops down into the middle. So that's your constructive plate margin. The decompression melting as the magma, sorry, no, not the magma, as the mantle rock solid but ductile flows up. It melts to produce the magma, which then forces its way in here to dikes. That's going to increase the buoyancy of this area. It's young and hot and therefore will rise up to form the ridge. And as the ridge then experiences that tension, either through ridge push or slab pull, that tension of pulling apart causes the rock to fracture along faults, and those faults, in this case, because it's tension, normal faults. In the case here, because it's compression, thrust faults. Okay, destructive, constructive. Next up, conservative. And the features in particular that are formed there are known as your transform faults. Oh, just realized I've forgotten to mark on this map where you get your constructive plate margins. Okay, so this is seafloor spreading, so not surprisingly, down the middle of the Atlantic Ocean and forming this shape that's very similar to the shapes of the outline of Africa, North America and South America. Then it comes around here into the Indian Ridge, South Indian Ridge, then up here to the Carlsberg Ridge. And this, we pick it up over here, pushing Australia away from the South Pole, then round here into the East Pacific Rise, and up here to this location here. And those are the locations where you get your constructive plate margin. Reference to places is often required, but it is always desired. If it's required and you don't include reference to places, you might drop down to level 1. You might. So make sure that you've got that locked well into your head. Okay, so let's have a look at this on an actual GIS map here. First of all, the zoom out, first of all, to give us a sense of the Mid-Atlantic Ridge. There it is, running down the middle of it. But this whole process doesn't happen on a nice flat piece of paper. It happens on a sphere, and therefore because of the really complex ways in which that spreading occurs along a sphere, it means that the ridge that comes down here is bisected by these transform faults before you come back to the ridge again. So you get a lot of these little stepped offsets all the way along here. And if you take a wee look at the whole of this, we'll zoom out, you can see very clearly here how all of those transform faults are found down here, the Mid-Atlantic Ridge. We follow it through here to the South Indian Ridge, up here to the Carlsberg Ridge, and you just get all of these transform faults occurring all along these constructive plate margins. We'll come back here into the Pacific, come on around here, and you can see them here as well. So it's all to do with this very, very complex way in which this spreading occurs on a sphere, and that's really what we want to bear in mind for these. Okay, let's come back to our little diagram here. So we're going to zoom in from that telescopic view here to have our ridge with our transform fault running across, another ridge, another transform fault running across, and another ridge. That's like that. So the plates in this point at a constructive plate margin, they are moving apart. That's the direction that the plates are moving. So in this case, the plates continue to move apart. That's the direction that they're moving. Let's put our arrows either side of the ridge here. The plates are moving apart. But what that means is because of the offsets here, that at certain points, the plates then are moving alongside each other in opposite directions, like here. Like here. And it's these that are our transform faults. This is when the plates that are spreading apart are moving at opposite directions. And what then tends to happen is that that's the location where you're going to get your earthquakes. The earthquakes are occurring whenever the rocks or the plates are moving in different directions in relation to each other. So they're moving in different directions here or along here where you're getting your normal faulting. The earthquakes are occurring along these normal faults. You'll also get a little bit of earthquake activity caused by the magma coming up here as well, as it forces its way into the rocks. So that's very much the pattern that you see there of these transform faults as they're found on ocean floors, and it's all to do with the accommodating of the complex spreading here that occurs on a sphere. If you have time, you can talk about these. Would be seafloor faults. They tend to be relatively simple features, as you can see from what we've seen on the screen. There are a couple of conservative margins, very significant ones on land. One of the most famous is the San Andreas Fault, and what you tend to have there is one main fault, the one main transform fault where they'll be moving alongside each other, but you'll get a lot of similar faults running alongside as well. This tends to be more of a broader fault zone rather than a single fault line. So on land, you'll get this kind of fault zone. So the earthquake that Leon and I experienced in San Diego in 2019 didn't occur on the actual San Andreas fault. It occurred in one of these secondary faults that's related to it as well. But that's only if you've got time. That's the main thing there with conservative. Okay, destructive, constructive, conservative, and finally, your collision zone. And when it comes to your collision zone, your main landform there, of course, is your fold and fault mountains. Your fold and your fault mountains. So let's have a wee look at the diagrams for that. I'm just loading up something here in Google Slides that I want to start off with showing you, I think. I'll just pull this over here now. Go full screen there for me, please. And we'll go into present mode. So the formation of the Himalayas is probably the easiest one to focus on here in this. And here we have, this is the one that I want to look at. So 90 million years ago, this is India down here. It's just separated off from South America. That's Africa. That's Australia there. Up here we have the rest of Asia. We put in our margins of that. This is a convergent margin or a destructive plate margin. So that's a little bit of your volcanic islands there that's forming. And down here, pushing away, you've got a constructive or divergent margin. So you have ridge push occurring there. You've got slab pull at the top, and India goes on a wee journey. And as it travels up 66 million years ago, 50 million years ago, it just begins to make contact with Asia and collides in. 35 million years ago, you can see the Himalayas beginning to form up here, and then that brings us to the present day. So in terms of our diagrams, what we want to do is really reflect a little bit of that journey. So I guess ideally there would be two diagrams for this, a before and an after. And the before diagram is going to be kind of like a version of what we're drawing here, right? So here is India. And this is our oceanic plate in between India, the Tethys Ocean, as it was called, and then the subduction that occurs underneath Asia, which we have here. Okay, let's just finish that off, like so. This, of course, is all underwater here, so we'll mark that on. And the direction of plate movement, that's going in this direction, that's going in this direction. This is India. And this is Asia. Asia, there we go. And we've got the subduction occurring down here, this slab pull, which is pulling the two together. And remember, way back here, we've got some ridge push as well. Now, at this stage, the accretionary wedge is very, very important, because what is folded up to form the Himalayas here is not so much the rock, but the sedimentary rock, the sediments that are formed here in the accretionary wedge and that are laid down here at the edge of India as rivers wash that down into the sea. So you have, sitting on top of that plate, a lot of sediment that forms into sedimentary rock, especially limestone. So that's probably around, say, 90 million years ago, 90 mega annum million years ago. And these plates are moving together. Now, at that point, of course, you're going to get your volcanoes occurring here. You're going to get something very, very similar to this, because that's that, basically. But the thing that we want to focus on here is the before of the collision. So, what then happens after that is that India keeps on being drawn closer and closer and closer by the slab pull and by the ridge push, and eventually India collides into Asia. Now, it's a continental crust, so it doesn't subduct, but it will go in underneath the landmass of Asia, doesn't subduct down. And there we go, we'll just draw it all out here. That's where it is at the moment. And then we've got the sediment here that has been folded and folded up to form the Himalayas. And then this is the rest of Asia here, which is part of the reason why the Tibetan plateau is so high, because you've actually got the part of the Indian plate underneath it, which is kind of bumping it up a little bit. Okay. So I think I would like to make those a little bit taller. That's probably why you should kind of sketch first, then ink, right, like so. And that's the situation that we have. Just one final thing to add on to this. The subducting plate has now detached and is no longer an active component in it all. The key thing here, as these two plates collide, you're getting a compression force. And that compression force is going to do two things. It's going to fold the rock, so it is going to get bent and distorted and twisted. That's why these are called fold mountains. But in actual fact, one of the key things that really drives these forward and this movement upwards is the faulting process. Now, the compression here, compression force is going to cause the thrust fault. You can see, move that down a bit, thrust fault there, pressing together, and one of them is going to move up in comparison to the other. So let me show you the video that illustrates that. There's a photograph of the thrust faults in action. Let's see, can I play this without... Yeah, there we go. Right, this is what some geologists do at university. They play with sand. That's really cool, isn't it? I thought you did that in primary school. That's just primary school teachers. No. You can do this as a geologist as well. And watch what happens. They're all getting very excited. Look, there you go. And it folds first of all, and then you can see the breaks. You can see the thrusts as the zigzag pattern there as that's moving up. Yes, it is being folded, but it is the thrusting that really gives that its ability to rise. And one of the things that we looked at for that was the earthquake in Nepal, which also caused that in 2015, this shifting up of motion. This is a satellite imagery which is used to look at the differences in the heights. So there's the changes in heights that have occurred as a result of that happening. I think, is this the video of it? We'll just play a bit of this. Yeah, it is. So you can see here the amount of motion. This is the people just wandering around, and you can see the different ways in which the plates are being moved. Imagine the amount of force that must be in place for this movement to be done. Here we come. There's the earthquake starting, and you see them moving. and then it moves a different direction. Just how much movement and motion there is, and overall that is thrusting upwards. So yes, you will get gradual folding over time, but periodically you get these massive big folds or faults that occur as a result of the earthquake occurring. So the plates are moving together there. The subduction is now below where you would be getting your decompression melting, so you don't get any volcanic activity here anymore. The rocks here are metamorphic and some limestones up towards the top, and the earthquakes that occur tend to be relatively close to the surface, which is part of the reason it makes them so dangerous. These earthquakes here can produce megathrust earthquakes if they occur really close to the surface with megathrust between the friction between the overriding and subducting plate, like they did in Japan. That can produce really large earthquakes, like that's your magnitude 8, magnitude 9 earthquakes, really close to the surface, which is going to produce tsunamis. Very, very dangerous. The earthquakes that occur here deeper down, remember the name of that, the Wadati-Benioff zone. The earthquakes that are occurring here are earthquakes that can be very, very deep. And even though they're big, because they're so deep, they tend to be less destructive. The same here, the Wadati-Benioff zone. The earthquakes that occur here tend to be much more surface earthquakes, but you don't tend to get the bigger earthquakes for these. You still can be big and noticeable, but you'll not get your magnitude 8 and 9s. The earthquakes here tend to be up to magnitude 7. Although there's some evidence that the likes of the San Andreas faults, if it all goes at once or a very, very large portion of it, could get up to magnitude 8, 9. But typically the magnitude 6, 7 would be the maximum here. And similarly here you can get some of those kind of magnitude 6, 7, but because they're really, really close to the surface, that makes them a lot more dangerous. Okay, so that's our overall view of the plate margins. The processes kind of related here to the overall processes that move the plates, then the processes that are going on for each one of the plate margins, and the landforms that are found as a result of those. This is physical geography, so it's extremely logical. This, then this, then this, therefore that. So for those of you who found the human geography a little bit kind of woolly and vague, this is you back into your comfortable territory here of it's science. It's this, then this, then this, therefore that. Those of you who are not scientists, who enjoyed the wriggle room of human geography, well, this is maybe not giving you that wriggle room, but it is very logical. So just go through list by list by list. I would almost suggest a good way of learning this is get some flashcards or post-its and put each stage on. I've got the stages numbered in the Google Slides on your website. Shuffle them up and put them in the right order, and just get yourself familiar with that and good terminology. Right, final thing to do as we come back here is to mark on some of our locations. So in terms of your conservative plate margin, any one of these green lines has got conservative plate margins. In terms of the major on land ones, you've got one there, and you've got one that runs through New Zealand, and also actually part of this one here in Turkey. That's a conservative plate margin. So that earthquake, the dreadful earthquake that occurred in Turkey and Syria earlier on this year, occurred along a conservative plate margin. In terms of collision zones, the classic collision zone is the Himalayas, which is just here. But in many ways, this is all a bit of a collision zone. This is collision here. This is complex. I don't really ever see them giving you too detailed a question in this area. The Mediterranean is very, very complex. Just for completeness sake, that's a constructive margin there. And as India collides in here, as the India is moving in this direction, it's accommodated by a couple of conservative plate margins there as well, as that moves past that. Please make sure that you can refer to places. You should be able to get a map like that and annotate it like that. Please practice your diagrams. You should be able to draw them like that too. Anyway, there's in the time it would take for one period in class, a summary of all the plate margins, processes and landforms. I hope that was helpful for you.